So, here's something worth thinking about as you settle in tonight. Right now, the bed is pushing up against you, and the earth underneath it is bending time. Not poetically, measurably. A clock at your feet runs very slightly slower than a clock at your head, because your feet sit a little deeper in the Earth's gravity. Over a lifetime, the difference is a few billionths of a second. Now take that effect and turn it up. Keep turning. There are places where time slows so much, seen from outside, that it seems to stop altogether. If you drift off somewhere along the way, that's perfectly fine. The ideas will still be here in the morning. So let's start where the story actually starts. Not with Einstein, with a country parson in Yorkshire and a very odd letter. His name was John Michel, and he was the rector of a parish church in Thornhill, a village in the West Riding of Yorkshire. He had trained at Queen's College, Cambridge, and he was one of those 18th century figures who seemed to have quietly done everything. He worked out that magnetic force falls off with the square of distance. He designed the torsion balance that Henry Cavendish would later use to weigh the Earth. After the Lisbon earthquake flattened the city in 1755, Michel wrote a paper arguing that earthquakes travel as waves through rock. That paper is more or less the founding document of seismology, and he was the first person to look at the sky statistically. There were far too many close pairs of stars for chance to explain. Double stars, he said, must actually be bound to each other. He was right, and it took decades for anyone to confirm it. And in 1783, he sat down and wrote a letter to Cavendish that was read aloud to the Royal Society in London. The reasoning in it is simple enough to follow lying down. Throw a ball upward and it comes back. Throw it harder and it takes longer to come back. Throw it hard enough, at about 11 kilometers per second from the surface of the Earth, and it never comes back at all. That number is called the escape velocity, and it depends on two things only: how much mass you're standing on, and how close you are to the middle of it. Now, Newton believed light was made of tiny particles. Corpuscles, he called them. And if light is made of particles, Michel reasoned, then light must have weight, and gravity must pull on it like it pulls on everything else. So what happens to a star so massive that its escape velocity climbs past the speed of light? The light would leave the surface. It would slow. It would fall back down. Michel worked out roughly how big such a star would need to be. Same density as the sun, he said, and about 500 times its diameter. And the light from a body like that could never reach us. He called them dark stars, and he pointed out something rather lovely about them, which is that you might still find one. If a dark star had a normal companion star orbiting it, you would see the bright one swinging around, apparently nothing at all. That is, almost exactly how the first black hole was eventually identified. It just took about 190 years. Here's the part that still catches people out. Michel's number was wrong in its reasoning and right in its answer. Light does not slow down and fall back. Light always travels at the same speed for everybody, which is a fact nobody would discover for another 120 years. And yet, Carl Schwarzschild solved Einstein's equations properly in 1916. The radius he found for the point of no return was the same radius Michel had calculated with his corpuscles and his 18th century arithmetic. Identical. The Newtonian sum gets the right answer for entirely the wrong reason, which is a thing that happens in physics more often than physicists enjoy admitting. 13 years later, in 1796, the French mathematician Pierre-Simon Laplace published the same idea in a book called Exposition of the System of the World. There is no evidence he had read Michel. He seems to have simply arrived there himself, as Laplace tended to. And then he took it out. The idea appears in the first edition and the second, and by the third edition, printed in 1808, it is gone. Laplace never explained why in print, so we're guessing, but the timing is suggestive. In 1801, Thomas Young had run light through a pair of narrow slits in London. He watched it produce interference bands. Particles do not do that. Waves do. Light was a wave. And nobody in 1808 had the faintest idea how gravity was supposed to act on a wave. So the dark star became an embarrassing loose end, and Laplace, sensibly enough, tidied it away. After that, the idea simply stops. For 120 years, nobody writes about it. There is no research program, no debate, no name for the thing. Michel's letter sat in the philosophical transactions of the Royal Society, entirely public and entirely unread. And the man himself was more or less forgotten until the 1970s, when astronomers went back and found him waiting there. The reason nothing happened for so long is not that the idea was too strange. It's that the tools were wrong. You cannot get to a black hole from Newton. You can get to the number, as Michel did, by a happy accident of algebra, but you cannot get to what the object actually is. In Newton's universe, space is a fixed stage, and time is a clock on the wall. Neither of them can be damaged. To reach the real thing, somebody had to break both, which brings us to a patent clerk in Bern. In 1905, Albert Einstein was working as a technical examiner in the Swiss Patent Office in Bern. He published a paper that took one strange experimental fact and followed it all the way down. The fact was that light always moves at the same speed no matter how fast you are moving when you measure it. Run toward a beam of light and it does not arrive faster. Run away and it does not arrive slower. Everyone gets the same number, always, about 300,000 kilometers per second. That sounds harmless. It isn't. Speed is distance divided by time. And if everyone measures the same speed for light, then distance and time have to bend to make the arithmetic work. Moving clocks run slow. Moving rulers shrink. Two events that happen at the same moment for you happen at different moments for somebody flying past. Time stopped being a universal river running at one rate for everyone and became something local, something that belongs to each object separately. And that immediately broke gravity. Newton's gravity is instantaneous. In Newton's picture, if the sun vanished right now, the Earth would swerve out of its orbit right now, this instant, with no delay at all. But Einstein had just spent a paper demonstrating that nothing outruns light, and he had shown that the word now does not mean the same thing in two different places. So the old theory of gravity and the new theory of motion could not both be true. One of them had to go, and it was not going to be the one that experiments kept confirming. It took him 8 years to fix it. He later said, the thought that unlocked everything came to him in the patent office. He called it the happiest thought of his life, which for Einstein counts as enthusiasm. The thought was this: a man falling off a roof does not feel his own weight. Sit with that for a second, because it is the whole thing. While you are falling freely, gravity is not something you experience. There is no force pressing on you anywhere. Astronauts on the space station are not weightless because they've escaped Earth's gravity, which is nearly as strong up there as it is down here, and they are weightless because they are falling continuously and missing the planet. Falling feels like nothing at all. It feels like being nowhere near anything. So Einstein turned the problem inside out. What if falling is not what happens when a force acts on you? What if falling is the natural state, the thing objects do when nothing is interfering with them, and the strange sensation is the other one? The pressure you can feel right now, the mattress against your back, the floor under a chair. That is a force. Something solid is pushing you off the path you would otherwise take. If falling is natural motion, then gravity is not a force at all. It's the shape of the paths. Mass bends the geometry of space and time around it, and everything else simply travels as straight as it can through the bent geometry. The Earth is not being tugged by the sun on some invisible string. The Earth is going straight ahead in a region where straight ahead happens to close into a loop. John Wheeler, who will meet properly later on, put it into one sentence that has never been improved on. Matter tells space-time how to curve, and space-time tells matter how to move. The equations that describe that took Einstein until November of 1915, and they nearly beat him. He made errors, published a wrong version, and withdrew it. And he spent the last weeks in a sprint against the mathematician David Hilbert, who was closing in on the same result from another direction. When he finally had it, he tested it on a problem that had been irritating astronomers for over half a century. Mercury's orbit doesn't quite close. The point where it swings nearest the sun creeps forward a little each time around, and most of that creep is explained by the pull of the other planets. But not all of it. A small remainder was left over, about 43 seconds of arc per century, which is a truly tiny angle. Astronomers had been trying to explain it for decades. One proposal involved an extra planet hiding close to the sun, which they had already gone so far as to name. Einstein put Mercury into his new equations, and out came the missing 43. And he wrote to a friend that he had been beside himself for days, and that something inside him had actually snapped. He said he had heart palpitations. Then came the test that made him famous. If mass bends space-time, starlight passing close to the sun should arrive slightly bent, which would shift the apparent positions of stars near the sun's edge. You can only see stars next to the sun during a total eclipse. So in May of 1919, 2 British expeditions went out to photograph one. Arthur Eddington took a team to the island of Principe off the west coast of Africa, and Andrew Crommelin took another to Sobral in northern Brazil. Principe was rained on for most of the eclipse. Sobral had better weather and, as it turned out, better plates. When the results were announced in London that November, they matched Einstein and not Newton, and the story went around the world in a day. Historians have argued ever since about how solid that particular measurement really was. Eddington set aside one troublesome set of plates, and the errors were uncomfortably large. Later, re-examinations of the original photographs have generally supported his conclusion, and eclipse measurements since have confirmed the bending very precisely. But at the time, the case was thinner than the headline suggested. None of that is the part that matters most here. The part that matters is quieter. Einstein's equations describe how much spacetime curves for a given amount of mass in a given amount of space, and there is nothing in them that says the curvature has to stop anywhere. Somebody was about to notice. His name was Karl Schwarzschild, and by 1915, he was one of the most respected astronomers in Germany, director of the Astrophysical Observatory at Potsdam. He was 41 years old, which is comfortably too old for military service, and he was a professor, which would have exempted him anyway. He volunteered. He served on the Western Front first, then the Eastern, calculating artillery trajectories for the German army in Russia. And it was there, in a field position on the Russian front in the winter of 1915, that a copy of Einstein's new paper reached him. Einstein had solved his own equations only approximately. He thought that was the best anyone was likely to manage, because the equations are 10 interlocking nonlinear differential equations, and they resist you. Within a few weeks, in a trench, Schwarzschild found an exact solution. He sent it to Einstein in a letter in December, apologizing for the intrusion. Einstein wrote back that he had not expected anyone to find the exact answer in so simple a form. And in January of 1916, he read the paper aloud to the Prussian Academy of Sciences in Berlin on Schwarzschild's behalf. What the solution describes is the shape of space-time in the empty region outside a single spherical mass that isn't spinning. A star, a planet, anything round and still. It is still the most used solution in general relativity, and every calculation of a spacecraft trajectory near a massive body eventually leans on it. And it has two places where the arithmetic falls apart. One is at the exact center, at zero distance from the middle, where the curvature runs away to infinity. The other is at a particular distance from the center, and that distance depends only on the mass. Twice the mass, twice the radius. It's now called the Schwarzschild radius, and for the Sun, it works out at just under 3 kilometers. For the Earth, it's about 9 millimeters. For a person your size, it's a length so small that no instrument built or imagined could resolve it. Look at those numbers, and you can see why nobody panicked. 3 kilometers from the center of the Sun is not out in space. It's buried under 700,000 kilometers of hot hydrogen, and Schwarzschild's solution only describes the empty region outside a mass, so at 3 kilometers deep, it simply doesn't apply. The troublesome radius was always tucked away somewhere the equations weren't valid. For any normal object, it looked like a bookkeeping artifact, a place the map went strange in a region there was no way to visit. And that was a perfectly reasonable thing to think for about 20 years. Schwarzschild sent a second paper a few weeks later, describing the inside of a star rather than the outside. He also, in the same months and the same trench, worked out a quantum problem about how electric fields split spectral lines. And then he got sick. He had contracted pemphigus, an autoimmune disease in which the body attacks the connections between its own skin cells. It was untreatable at the time. He was discharged, sent home, and died on the 11th of May, 1916, at the age of 42. He had about 4 months between finding the solution and dying of a condition he picked up on the front where he found it. His son Martin, then 4 years old, grew up to become an astrophysicist too, and spent his career in America working out how stars evolve. The object his equations describe would not be understood for another 45 years. Einstein himself never accepted it. As late as 1939, he published a paper arguing that a Schwarzschild singularity could not exist in physical reality. Matter, he said, would simply refuse to compress that far. It's one of the very few places where he was flatly, demonstrably wrong about his own theory. Which brings us to what that radius actually is, and to the mistake that held everything up. For decades, both of the places where Schwarzschild's mathematics broke were called singularities, and physicists treated them as the same kind of problem. They are not the same kind of problem, and telling them apart is the single most useful idea in this whole subject. When a calculation blows up and gives you infinity, there are two possibilities. One is that something genuinely extreme is happening. The other is that you have described a perfectly ordinary situation using the wrong grid. Think about lines of longitude. They're a fine way to say where you are for most of the planet, but they all converge and meet at the North Pole. At the pole itself, your longitude is undefined. Every value is correct simultaneously. The mathematics falls over, and yet nothing whatsoever is wrong with the North Pole, and it is a cold, ordinary patch of drifting sea ice, and if you stand there, you will notice nothing strange underfoot. The failure is in the map, not the ice. The Schwarzschild radius is the North Pole. The center is not. Working that out took a long time and several people who did not quite realize what they had. The French mathematician Paul Painlevé did it in 1921. The Swedish ophthalmologist and physicist Alvar Gullstrand did it in 1922. Both wrote down alternative coordinates in which nothing went wrong at that radius at all. Neither of them concluded from this that the problem had been imaginary. Arthur Eddington, in a paper in 1924, wrote down a change of variables that removes it completely, and he appears to have used it for something else entirely and moved on. The first person to say it out loud was Georges Lemaitre. He was a Belgian priest and mathematician, better known for proposing that the universe began in an expanding state. In 1932, he stated plainly that the singularity at the Schwarzschild radius is fictitious, an artifact of the coordinates and nothing more. Almost nobody noticed. David Finkelstein, an American physicist, rediscovered Eddington's transformation in 1958, and this time understood what it meant. The surface is not a place where physics breaks. It is a one-way membrane. Things can cross it inward, and nothing crosses it outward. 2 years later, Martin Kruskal in America and George Sekeres in Australia independently produced the full description, and it shows the entire space-time at once, with no artificial edges anywhere. 44 years. From an exact solution in a trench in 1916 to a clear understanding of what that solution was describing in 1960. And the delay was not caused by any missing observation or any new mathematics. It was caused by everyone using an awkward set of coordinates and mistaking the awkwardness for the world. So what is actually there at that radius? Nothing. That's the honest answer, and it's the one people find hardest to accept. There is no surface, no membrane you could touch, no shell of material, no shimmer, no boundary you would see approaching. If you fell through the event horizon of a sufficiently large black hole, you would not feel a thing. There would be no sensation of crossing, no jolt, no moment. You would not be able to tell that it had happened. The stars ahead of you would still be there. Your watch would keep ticking at 1 second per second, because your watch always ticks at 1 second per second, everywhere, for everyone. The horizon is not a thing. It's a boundary in the causal structure. It's the surface separating the events that can eventually send a signal out to the distant universe from the events that cannot. And that definition has a genuinely unsettling consequence, which is that the horizon depends on the future. To know whether a flash of light escapes, you have to know where it ends up. And that means knowing the entire later history of the space-time. So the location of a horizon is not something you can determine by measuring anything locally, right now, at that spot. It's determined by what will happen. Say a large shell of matter is falling inward toward a black hole. The horizon starts growing outward to meet it before the matter arrives. It expands in anticipation of mass it hasn't swallowed yet. Nothing is violating cause and effect. It's just that the horizon was never a local object in the first place. And asking where it is at this instant is a slightly ill-posed question. That is a lot to accept about a place where nothing happens. And it gets stranger when you ask about time. You already know the effect at the heart of this, because your phone uses it every day. The satellites of the global positioning system carry atomic clocks, and those clocks do not agree with the ones on the ground. Two separate things are happening to them at once. They're moving fast, about 14,000 kilometers per hour, which makes their clocks run slow. And they're 20,000 kilometers up, higher in Earth's gravity, where space-time is less curved, which makes their clocks run fast. The two effects work in opposite directions, and they don't cancel. The gravitational one wins. Net result, A GPS satellite clock gains about 38 millionths of a second every day compared to a clock in your kitchen. That sounds negligible. It isn't. Position is worked out from the travel time of light, and light covers 30 centimeters in a billionth of a second. Left uncorrected, the error would grow by about 10 kilometers a day, and the entire system would be worthless inside an afternoon. So the correction is built in, and has been since the first satellites went up. Einstein's theory of gravity is running quietly in the background of every navigation app on Earth. Now push that effect, take a clock and lower it toward a black hole. As it gets closer to the horizon, it runs slower and slower compared to yours, and the slowdown has no limit. Right at the horizon, from your point of view far away, it stops. So imagine watching something fall in, a probe, a star, anything. As it approaches, its clock crawls. Its motion crawls with it. The light it sends you takes longer and longer to climb out, and stretches on the way. It slides from visible light to infrared to radio, and then to wavelengths with no name. It gets dimmer as the photons arrive further and further apart, and it never quite reaches the horizon. Not in a million years. Not in a trillion. From the outside, in this coordinate system, nothing ever finishes falling in. That's why the Soviet School of Astrophysics, working under Yakov Zeldovich and Igor Novikov in Moscow through the 1960s, called these objects frozen stars. Everything about them appeared stuck at the moment of collapse, hanging there forever. It's a good name, and it describes exactly what the equations say a distant observer would see. Except you wouldn't see it. Not really. The freezing takes hold fast, and the light fades steeply. For a black hole a few times the mass of the sun, the infalling object becomes invisible in a fraction of a millisecond. The last photon that ever gets out almost immediately. The eternally frozen image is a mathematical limit, not a view. In practice, things fall in and go dark quickly. Meanwhile, ride along with the thing that's falling. Your clock ticks normally. It always does. You cross the horizon in a finite amount of your own time, without incident, and you reach the center in a finite amount of time after that. For a black hole of a few solar masses, the whole trip from horizon to center takes well under 1,000th of a second. There is no freezing. There is no waiting. Nobody has ever experienced hovering at a horizon forever, because nothing does. So which one is true? Does the object fall in, or does it hang there for eternity? Both. And the reason that isn't a contradiction is the thing Einstein worked out in 1905. There is no universal present moment shared between two separated observers, at the same time as is not a fact about the universe. It's a relationship between a pair of viewpoints. And near a black hole, those viewpoints diverge so violently that they stop having any useful overlap at all. Asking what is happening right now at the horizon, from your armchair, is asking a question that has no single answer. Not because we're being coy, because the word now ran out of meaning somewhere on the way in. While we're here, one popular claim needs correcting, because it turns up constantly. You'll hear that as you fall into a black hole, you would look back and watch the whole future history of the universe. It would play out above you, in fast forward. For someone in ordinary free fall, that's not right. You catch up with only a finite amount of the outside universe's history on the way down. The infinite version applies to something rather different, an observer who hovers just outside for an extremely long time and then leaves. That takes an unimaginable amount of thrust, and it is not what falling means. Falling in is quick, quiet, and rather unremarkable, right up until it isn't. But none of this mattered yet, because in the 1930s, nobody believed a real star could ever get into that state. Something always stops a collapse. Something has to. And then a 19-year-old on a boat found the place where nothing does. His name was Subramanian Chandrasekhar. He was born in Lahore in 1910 and grew up in Madras. And in July of 1930, he boarded a ship for England to begin research at Cambridge. The voyage took the better part of 3 weeks. He spent it doing a calculation. The problem he picked at was white dwarf stars. When a star like the sun runs out of fuel, it sheds its outer layers. The core collapses down to about the size of the Earth. It's so dense that a teaspoon would weigh several tons. In 1926, Ralph Fowler had worked out what holds one up. It isn't heat. It's a quantum rule called the Pauli exclusion principle, which forbids two electrons from occupying the same state. Squeeze the electrons together, and they resist, not because they repel each other, but because there is nowhere left for them to be. That resistance is called degeneracy pressure, and it doesn't care about temperature. A white dwarf can cool forever and still hold itself up. Chandrasekhar noticed that Fowler had left something out. Squeeze harder, and the electrons have to move faster. Squeeze hard enough, and they approach the speed of light, and once they do, relativity takes over. A particle near light speed cannot go meaningfully faster, no matter how much energy you give it, so the pressure stops rising the way it used to. And it keeps rising, but more slowly. Gravity does not slow down at all. So what happens to a star heavier than that? Does something else step in, or does the collapse simply continue? Somewhere the two curves cross, and he worked out where. Above roughly 1 4/10 times the mass of the Sun, electron degeneracy pressure cannot win. Not because the star is too hot or too cold or badly arranged, but because no arrangement exists. The number is now called the Chandrasekhar limit, and it's one of the few genuinely fundamental thresholds in astrophysics. It's set by nothing but the mass of a proton, the charge of an electron, and the constants of nature. He was 19. He did it on a boat, and nobody wanted it. On the 11th of January, 1935, the Royal Astronomical Society met at Burlington House on Piccadilly in London. Chandrasekhar, now 24, was on the program to present his result. Arthur Eddington was scheduled immediately after him. Eddington was the most influential astrophysicist in Britain. He was the man who had gone to Principi and made Einstein famous. And he was the man who had worked out how stars hold themselves up against their own weight in the first place. He had been visiting Chandrasekhar's rooms regularly while the work was being done, reading the pages, discussing the calculations, arranging for extra computing time. Chandrasekhar had no reason to expect anything other than support. Eddington stood up and demolished him in front of the room. He called the result a reductio ad absurdum. He said there ought to be a law of nature to prevent a star from behaving in this absurd way. He argued that Chandrasekhar had combined relativity and quantum mechanics illegitimately, and that the relativistic treatment of the electrons was simply not valid. The whole conclusion, he said, followed from a mathematical mistake rather than from the universe. Chandrasekhar was given no chance to respond. He wrote afterward that he went home that night and did not know whether to continue in astronomy at all. It's worth being fair to Eddington here, because the easy version of this story makes him a bully, and that isn't quite it. He had a real technical objection, rooted in his own unorthodox ideas about how quantum mechanics and relativity ought to fit together. He had been developing those ideas for years, and would keep developing them to the end of his life. He genuinely thought Chandrasekhar's electrons had been treated wrongly. He was mistaken, and the mistake was his. But he was not being dishonest, and he and Chandrasekhar remained personally cordial for the rest of Eddington's life, which says something about both of them. The damage was done anyway. Chandrasekhar went looking for backup and found that the physicists agreed with him privately and would not say so publicly. Niels Bohr thought Eddington was wrong. Wolfgang Pauli thought Eddington was wrong. Leon Rosenfeld wrote to say the argument was nonsense. None of them wanted to fight the great man in the astronomical journals over a question they regarded as belonging to somebody else's field. So the astronomers, who were the ones who would actually need this result, went on hearing only Eddington. Chandrasekhar packed up the whole subject. He wrote it into a book, published in 1939, and then simply stopped working on stellar structure. In 1937, he moved to the United States, to Yerkes Observatory and the University of Chicago, and stayed there for the rest of his career. He developed a habit of spending roughly a decade on a field, writing the definitive book about it, and then leaving it for something else entirely. Stellar dynamics, radiative transfer, hydrodynamic stability. He came back to relativity in his 60s and produced a work called The Mathematical Theory of Black Holes. It arrived in 1983, 48 years after Burlington House, and that same year he received the Nobel Prize in Physics, in part for the calculation he had done on the boat. He was 73. The question left hanging in 1935 was simple enough. If a stellar core above the limit cannot be held up by electrons, what holds it up instead? For a while, there was an excellent answer. In 1932, James Chadwick in Cambridge had found the neutron, the neutral partner to the proton, in the atomic nucleus. 2 years later, at Caltech, Walter Body and Fritz Zwicky published a one-page abstract that is one of the most audacious documents in the history of astronomy. They proposed that the enormously bright stellar explosions occasionally seen in other galaxies represent the transition of an ordinary star into a star made of neutrons. They coined the word supernova in the same breath. They suggested cosmic rays came from these events. Almost everything in that abstract turned out to be right, and almost nobody took it seriously at the time, partly because Zwicky had a talent for making enemies that was as remarkable as his physics. A neutron star squeezes something like the mass of the sun into a ball roughly 20 kilometers across. The whole object is essentially one atomic nucleus the size of a city, and it holds itself up the same way a white dwarf does, by the exclusion principle. Except now, it's the neutrons that have nowhere left to go. Neutrons are nearly 2,000 times heavier than electrons, so they can hold up far more. But you can already see the shape of the problem. It's the same argument again. In 1939, Robert Oppenheimer at Berkeley, working with George Volkoff and building on earlier equations from Richard Tolman, calculated the maximum mass a neutron star could have. Their number came out low, under 1 solar mass, because they had no way to include the strong nuclear force, which nobody understood yet. The modern figure is somewhere around 2 to 2.5 times the mass of the Sun, and the exact value is still an open research question. It depends on how nuclear matter behaves at densities we cannot reproduce anywhere on Earth, and the number matters less than what it means. There is another ceiling, and above it, once again, nothing known can hold the weight. So Oppenheimer took the last step. With a graduate student named Hartland Snyder, he wrote a short paper titled On Continued Gravitational Contraction. And he asked what happens if nothing stops the collapse at all. They stripped the problem down to a sphere of dust with no pressure, which made it exactly solvable, and they followed it all the way in. What they found was the frozen star, described properly for the first time. From outside, The collapsing star slows as it shrinks, its light reddens, and it appears to hang just short of its own Schwarzschild radius forever. From the point of view of matter riding the surface downward, the collapse takes a finite and rather short time and simply continues. The star, in their words, closes itself off from any communication with a distant observer. Only its gravitational field persists. That is a black hole, described correctly, in 1939. The paper appeared in the first September issue of Physical Review, dated the 1st of September, 1939. That morning, German forces crossed the Polish border. It's hard to imagine worse timing. Within 2 years, Oppenheimer was running the theoretical division of a bomb project, and he never wrote about gravitational collapse again for the rest of his life. And in the same issue of the same journal, on adjacent pages, sat a paper by Niels Bohr and a young American named John Wheeler, working out the mechanism of nuclear fission. The two most consequential papers in that issue were about the two things that would define the next 30 years. Only one of them got any attention at all. Wheeler, as it happens, thought Oppenheimer was wrong. He said so, in public, for years. At the Solvay conference in Brussels in 1958, he argued that continued collapse could not be the true fate of matter, and that some new physics must intervene. Oppenheimer disagreed from across the room. It's one of the odder facts of this story that the man who spent the 1950s objecting to black holes is the man everybody now associates with the phrase. Two things happened in the 1960s that dragged the whole subject out of the filing cabinet. The first arrived in 1963. Astronomers had been puzzling over a handful of radio sources that looked like faint blue stars, but behaved like nothing stellar. One of them, catalogued as 3C273, was studied by Martin Schmidt at Palomar Observatory in California. He stared at its spectrum for weeks. The lines matched nothing. Then he tried assuming they were ordinary hydrogen lines shifted enormously far toward the red, and everything snapped into place at once. And the object was billions of light years away. To look as bright as it did from that distance, it had to be pouring out more energy than an entire galaxy, and its brightness flickered over weeks, which meant the source could be no larger than a few light weeks across. Something smaller than the solar system was outshining 100 billion stars. Nuclear fusion cannot do that. Nothing chemical or nuclear comes close. Only one process anyone could think of had enough efficiency. Matter falling into an extremely deep gravitational well, giving up a large fraction of its rest mass on the way down. Suddenly, gravitational collapse was not a philosophical curiosity. It was an observation that needed explaining, and it was sitting in the data. The second thing happened in 1967, in a field outside Cambridge. A graduate student named Jocelyn Bell had helped build a radio telescope out of wire and wooden posts across 4 acres. She was going through the paper chart recordings by hand, hundreds of meters of them, and she noticed what she called a bit of scruff. It came back. It turned out to be a radio pulse repeating every 1 3/10 seconds with extraordinary precision. The team briefly and half-seriously labeled the source LGM-1 for little green men. Then, they found a second one somewhere else in the sky and concluded that the universe was probably not full of independent alien beacons. What they had found was a neutron star, spinning, sweeping a beam of radio waves past the Earth like a lighthouse. Bod and Zwicky's absurd 1934 suggestion was real, and here was one on a chart in Cambridge. The Nobel Prize for that discovery went to Anthony Hewish and Martin Ryle in 1974. Bell was not included, which was controversial then and is considered indefensible now. And she has said, repeatedly and with more grace than the situation deserves, that she does not mind. So by 1967, the ceiling below had been confirmed, and the object above had been observed. What was still missing was a name. The phrase black hole appears in print for the first time in a short article by the science journalist Anne Ewing. It ran in the Science newsletter on the 18th of January, 1964, reporting from a meeting in Cleveland. Who said it in that room is not recorded. The physicists at the time were calling these objects gravitationally completely collapsed objects, which is accurate and unusable, or frozen stars, which was the Soviet term, and slightly misleading. John Wheeler used the short version in a lecture in New York in late 1967, and by his own account, he did not invent it. He said someone in an audience had thrown it out during a discussion, that he had been groping for something shorter for months, and that he adopted it gratefully. From him, it spread, because Wheeler talked to everyone and taught nearly everyone. He had a gift for this. Wormhole is his. Quantum foam is his. The phrase about black holes having no hair is his, and it caused genuine offense in France, where the direct translation was considered indecent and the term was resisted for years on those grounds. Wheeler thought the fuss was funny and kept saying it. Naming a thing sounds trivial. It isn't. Between 1916 and 1967, the subject had no handle, and the moment it got one, the field detonated. The years from about 1963 to 1974 are still called the golden age of black hole physics, and almost everything in the rest of this story comes from them. Roger Penrose fired the first shot, and the idea came to him while crossing a road. It was the autumn of 1964. Penrose, then at Birkbeck College in London, was walking to the underground station with a colleague, talking about something else entirely. They stepped off the curb, and in the middle of the side street, the conversation paused for traffic, and something surfaced. On the far pavement, the conversation resumed, and the thought went under again. He noticed later that afternoon that he felt oddly elated with no idea why, went back through his day mentally, and retrieved it. The problem he had been chewing on was this. Everything anyone knew about collapse assumed perfect spherical symmetry. Oppenheimer and Snyder's dust ball was a perfect sphere. Schwarzschild's solution is a perfect sphere. And the universe does not contain perfect spheres. Real stars are lumpy. They rotate. They wobble. Wheeler, among others, had made the standard objection. In any realistic collapse, the infouling matter would miss the exact center, swirl past it, and fly back out. The singularity was an artifact of an impossible idealization. Reality would find a way to bounce. What Penrose had was a way to prove that it wouldn't, without assuming any symmetry at all. He called the key idea a trapped surface. Imagine a closed surface, any shape, somewhere in a collapsing region, and imagine a flash of light emitted from every point on it at once. Normally, the outward-going light spreads out, and the surface it forms grows larger. But if the gravity inside is strong enough, the outward-going light front gets smaller. Not the inward-going one, which obviously shrinks. The outward one. Light doing its absolute best to escape, and still converging. Once that has happened, Penrose showed, it's over. Given some very mild assumptions about matter not having negative energy, and given that the geometry doesn't do anything pathological, a singularity must form. No symmetry required. No perfect sphere. No careful arrangement. If a trapped surface forms anywhere, the collapse cannot be undone by any amount of swirling or lumpiness or spin. The paper is 3 pages long. It appeared in Physical Review Letters in January of 1965, and it is one of the most important 3 pages in 20th century physics. Stephen Hawking, then a graduate student, read it, and he realized the argument could be run backwards in time and applied to the expanding universe instead of a collapsing star. Together, over the following 5 years, they produced a set of theorems showing that under general relativity, the universe itself must have begun in a singularity as well. And Penrose's theorem carries a second lesson that takes some getting used to. Inside a black hole, the singularity is not a place. It's a time. Outside the horizon, the distance from the center is a spatial direction. You can move toward it or away from it, or stay put, as you can with any direction. Cross the horizon, and the mathematics does something startling. The radial direction and the time direction swap roles. Decreasing distance from the center becomes the future, which means you cannot avoid the singularity by steering. You cannot hover, you cannot orbit, you cannot fire an engine hard enough to hold position any more than you can hold position against next Thursday. Every possible path leads there. It's not in front of you, it's ahead of you, in the only sense of ahead that time allows. There's a detail here I find quietly wonderful. Once inside, the longest you can survive is achieved by doing nothing at all. Free fall gives you the maximum. If you fire your rockets and struggle against it, you shorten the time you have left. The universe's advice in that situation is to relax, which is both true and completely useless. For a black hole a few times the mass of the sun, the maximum is measured in millionths of a second. For the giant at the center of our galaxy, it's a little under a minute. And what does singularity mean, really? It does not mean a point of infinite density sitting there like a marble. It means the equations stop producing answers. It's a signpost saying the theory has been pushed past the range where it works. Nobody in the field believes there is an actual infinity in there. What almost everyone believes is that a full theory of quantum gravity will replace that point with something finite and strange. We do not have that theory. Penrose received the Nobel Prize in Physics in 2020 for that theorem, 55 years after crossing the road. Everything so far has assumed the thing isn't spinning, and nothing in the universe isn't spinning. Stars rotate. When a rotating star collapses, conservation of angular momentum takes over. It's the same rule that makes a skater speed up when she pulls her arms in. Shrink a slowly turning ball of gas down to a few kilometers across, and it will be whirling. So Schwarzschild's beautifully simple solution describes an object that has never existed. The rotating version took 47 years, and when it arrived, it came from a New Zealander named Roy Kerr, working at the University of Texas in 1963. The difficulty is not conceptual. It's that giving up spherical symmetry turns Einstein's equations from very hard into something close to hopeless, and generations of people had tried and failed. Kerr found the exact solution for a spinning, uncharged mass, and it fits on a page. He presented it that December at the first Texas Symposium on Relativistic Astrophysics in Dallas, a meeting convened largely because of the quasar problem. By several accounts, the room did not much care. Astronomers had come to hear about energy sources, and they drifted off during the mathematics. Then the Greek relativist Achilles Papapetro stood up afterward and told the audience, with some heat, what they had just failed to listen to. Chandrasekhar, decades later, described the Kerr solution as the most shattering experience of his scientific life, not because the mathematics was beautiful, though it is, but because of what it implied. A short expression written down by one person in 1963 turns out to describe, exactly and completely, every one of the uncountable enormous objects scattered through the universe. Not approximately. Exactly. And that completeness is itself one of the strangest facts in this subject. It has a name. Over the following decade, Werner Israel, Brandon Carter, and David Robinson proved a series of results collectively known as the no-hair theorem. A black hole in equilibrium is described entirely by three numbers: its mass, how fast it spins, and its electric charge. That's the whole list. And the charge doesn't matter in practice. A charged black hole sitting in a universe full of loose electrons and protons would pull in whatever neutralizes it within moments. So two numbers, mass and spin. Think about what that erases. Take a star made of hydrogen and helium, with a particular chemical history, a particular magnetic field, sunspots, layers, a rotation profile that varies with depth. Collapse it. What remains is a mass and a spin. Now take an equal mass of something completely different, a mountain of iron, a cloud of neutrinos, a very large library, and collapse that instead. The result is identical, not similar. Identical in every measurable respect, forever. Nothing else in physics does this. Everything else keeps a record of what it used to be. Burn a book, and the ash is scrambled. But in principle, every particle of smoke still carries the information, and a sufficiently patient demon could reconstruct the page. A black hole appears to actually delete it. Wheeler's phrase for it was that black holes have no hair, meaning no distinguishing features, no stray details left over. Hold on to that, because in about 40 years it becomes the biggest problem in theoretical physics. There's a related question people ask constantly, and it deserves a proper answer. What is a black hole actually made of? Where did the star go? The usual reply is that all the mass is crushed into an infinitely dense point at the center. And that reply is really just a restatement of the place where the theory stopped working, dressed up as a description. A better answer, and the one Wheeler liked, is that a black hole is not made of anything at all. It's a region of curved space-time that holds itself together. The gravitational field there is strong enough to act as its own source, and it persists without any matter propping it up. Wheeler called this mass without matter, and he spent years exploring whether a bundle of pure field could hold itself in shape. So the star that collapsed is not sitting inside, compressed into a pellet. From the outside, there is nothing to point at. And from the inside, the matter has already gone where everything inside goes, which is not a place but a moment, and the moment is already past. Then there's density, which is where most of the popular writing goes wrong. You'll hear that black holes are unimaginably dense, and for the small ones that's fair. Take the horizon volume of a black hole a few times the mass of the sun, divide, and the average density comes out around that of nuclear matter. But density behaves strangely here. The mass of a black hole grows in step with the radius of its horizon, and volume grows with the cube of the radius, so the average density falls as you go up in size, and it falls fast. Work it through, and a black hole of roughly 100 million solar masses has an average density comparable to water. In a purely arithmetical sense, you could float it. Go larger still, out toward the mass of everything in the observable universe, and the figure comes down to something like the air in this room, which raises a question that sounds silly and isn't. If you spread ordinary air thinly across a large enough volume, would it collapse? It would. Enough of anything, arranged over a wide enough region, closes a horizon around itself. Density is not what makes a black hole. Enough mass inside a small enough radius makes a black hole, and for very large masses, the radius does not have to be small by any human standard. So the image of a tiny, impossibly compressed dot describes the small ones, and the big ones are the reverse of what you would guess. Sagittarius A star has a horizon wider than the orbit of Mercury, and an average density well below that of the Sun, none of which tells you what is inside. Nothing does yet. That question has no experimental answer, and may never have one, because whatever is in there cannot send anything out. It is the only region in the universe permanently sealed off from the rest of it, and we are working entirely from the shape of the boundary. The spinning solution brings some new geography with it. Around a rotating black hole, there's a region outside the horizon called the ergosphere. Inside it, space-time itself is being dragged around so forcefully that standing still becomes impossible. Not difficult, impossible. There is no amount of engine power that lets you hover at a fixed point with respect to the distant stars. The fixed points have been swept away. You can still escape outward, and you can still fall in. You simply cannot avoid going around. This effect is called frame dragging, and it's not exotic. The Earth does it too, faintly, and it has been measured. Gravity Probe B was a satellite carrying 4 extraordinarily precise gyroscopes. It flew from 2004 to 2011, specifically to detect the Earth twisting the space around it, and it found the twist at roughly the predicted size. Laser ranging off the LAGEO satellites had already found hints of the same thing. Our planet drags space-time around by a few thousandths of an arc-second a year. A spinning black hole does it hard enough to make rest meaningless. And there is something you can do with that. In 1969, Penrose worked out a way to steal energy from a spinning black hole. Drop an object into the ergosphere and split it in two. Arrange things so that one piece falls in on a path that carries negative energy as seen from far away. The other flies back out. The escaping piece leaves with more energy than the whole object had going in. The difference has come out of the hole's rotation, which slows very slightly. You have not created anything, and you have withdrawn from a very large battery. For a maximally spinning black hole, the energy stored in the rotation is something like 29% of its total mass energy. That is an absurd quantity by any standard humans are used to. In 1977, Roger Blandford and Roman Zanajek found a version that works with magnetic fields threading the ergosphere instead of thrown rocks. And that mechanism is now the leading explanation for the enormous jets that shoot out of the centers of active galaxies at nearly the speed of light. Those jets are, on the best current understanding, black holes losing their spin. Which brings us to a rather practical question. If the thing emits nothing at all, how did anybody ever find one? You don't look at the black hole. You look at what's falling in and at what's orbiting nearby. Gas approaching a black hole almost never falls straight down because it almost always has some sideways motion to begin with, so it goes into orbit instead and settles into a flat disk, and the disk slowly drains inward as friction and magnetic stresses in the gas transport angular momentum outward. That inward drain releases gravitational energy, and it releases a lot of it. The inner regions of an accretion disk around a stellar mass black hole reach temperatures of millions of degrees, and matter that hot glows in X-rays. X-rays don't reach the ground. Our atmosphere absorbs them, which is excellent for biology and inconvenient for astronomy, so this entire field had to wait for rockets. In 1962, a team led by Riccardo Giacconi flew a detector above the atmosphere for about 6 minutes and found the first X-ray source outside the solar system. 2 years later, another rocket flight picked up a strong source in the constellation Cygnus, and it was catalogued as Cygnus X-1. In December of 1970, a small satellite called Uhuru was launched from an Italian platform off the coast of Kenya on the anniversary of Kenyan independence. Uhuru is the Swahili word for freedom. It was the first satellite dedicated to X-ray astronomy, and it mapped hundreds of sources, and it watched Cygnus X-1 flicker on timescales of a fraction of a second. Fast flickering means a small source, for the same reason a large object cannot change brightness all over faster than light can cross it. Whatever was making those X-rays was no more than a few 100 kilometers across. Then, the optical astronomers found the companion. Sitting at the same position was a hot blue supergiant star, and that star was wobbling, swinging around something invisible every 5.5 days. From the wobble, you can work out how heavy the invisible partner is, and the answer was far too heavy to be a neutron star. Current best estimates, revised upward in 2021 when the distance to the system was remeasured, put it at roughly 20 times the mass of the Sun. Look at what that method actually is: a bright star orbiting nothing visible, and the nothing weighed by the swing. That is precisely, in every detail, the detection strategy John Michel proposed in his letter in 1783. It took 190 years and a satellite, but the country parson's idea is how the first one was found. It was not immediately convincing to everybody. In 1974, Stephen Hawking and Kip Thorne made a bet about it. Hawking took the position that Cygnus X-1 was not a black hole, which he cheerfully admitted was insurance. And he had spent his career on the theory. If they turned out not to exist, he wanted something out of it. The stake was a magazine subscription in either direction, a satirical British one if Hawking won, and an American one of a different character if Thorne did. By 1990, the evidence had become overwhelming. Hawking was visiting Caltech and found Thorne's office empty. He let himself in and signed the concession on the framed document. Thorne got his subscription, to the reported irritation of his family. Now for the misconception that outlasts all the others, which is the idea that black holes suck. They don't. There is no vacuum, no pull that's different in kind from any other pull, no reaching out. Gravity depends on two things, and always has. How much mass is there, and how far away are you? So run the thought experiment. Take the Sun and replace it, this instant, with a black hole of exactly the same mass. What happens to the Earth? Nothing. The orbit does not change, not by a meter, not by a second. The Earth would go on tracing the same ellipse it has traced for 4.5 billion years. At a distance of 150 million kilometers, the gravitational field of a solar mass is a gravitational field of a solar mass. It makes no difference whether that mass is spread over 700,000 kilometers of plasma or squeezed into 3. It would get extremely dark and extremely cold, and the consequences for everything alive would be total, but orbitally it would be a quiet afternoon. The only difference a black hole makes is that you can get closer. With the Sun there, you run into the surface at 700,000 kilometers, and that's the end of the approach. With the black hole there, you can keep going in, and the field keeps strengthening the whole way, because there's no longer anything in your path. That's it. That's the entire difference. Not a stronger grip, a shorter obstacle. Getting closer does change what orbits are possible, though, and here general relativity departs from Newton in a way that matters enormously. In Newton's universe, you can orbit at any distance you like. Get closer, go faster, and you're fine. Around a black hole, there's a floor. For a non-rotating one, it sits at 3 times the Schwarzschild radius, and it's called the innermost stable circular orbit. Inside that boundary, there are no stable orbits at all. Nudge a circling object even slightly, and it does not settle back, it spirals in. Which is why accretion disks have a sharp inner edge, and why the gas doesn't just sit there in a ring forever waiting. Go a little closer still, and you reach the photon sphere, at 1.5 Schwarzschild radii. There, gravity bends light so much that a beam aimed sideways travels in a circle. Light orbits there. It's unstable, so nothing stays for long. But that thin shell of circling light turns out to be exactly what we photographed in 2019. We'll get to that. So what would falling in actually do to you? The answer depends entirely on size, in a way almost nobody guesses correctly. Gravity gets stronger as you get closer. That means your feet, if you're falling feet first, are being pulled harder than your head. The difference between the two is called a tidal force, and it's the same effect that raises the oceans on Earth twice a day. Near a black hole, it becomes severe. Your feet accelerate away from your head. You're stretched lengthwise while being squeezed inward from the sides, because all the paths are converging on one point. Hawking called this spaghettification, which is not a technical term and has been impossible to dislodge. Here's the counterintuitive part. The tidal force at the horizon is weaker for bigger black holes, much weaker. It falls off as the square of the mass, so a hole 1,000,000 times heavier has a horizon 1,000,000,000,000 times gentler. Fall toward a black hole of 10 solar masses, and you'd be torn apart thousands of kilometers before you reached the horizon. You would never see the inside. But the black hole at the center of our galaxy has about 4,000,000 times the mass of the Sun. Its horizon is roughly 12,000,000 kilometers out from the center. The curvature there is spread over such a vast scale that you would cross it entirely intact, feeling nothing whatsoever, with plenty of time left. The stretching would come later, deeper in, and it would come quickly at the end. But the crossing itself would be uneventful. The largest ones are gentlest at the door, and worst inside. That's not a paradox, it's just geometry. But it does mean that everything you may have absorbed about being shredded at the edge is describing the small ones. Stars get shredded regularly, and we watch it happen. When a star wanders too close to a large black hole, the tidal forces pull it apart, and the debris does something specific. Roughly half the material gets flung out on escape trajectories and leaves. The other half falls back, forms a temporary accretion disk, and lights up, producing a flare that brightens over weeks and fades over months or years. These are called tidal disruption events, and dozens have now been recorded in other galaxies. Somewhere out there, on any given night, a star is coming apart, and we can see the light of it. It's worth stopping here to say where these objects come from, because they don't all come from the same place, and one of the categories is a real mystery. The ordinary ones form when a massive star dies. Anything above roughly 20 times the mass of the Sun is a candidate. The core runs out of fuel, the support gives way, and the inner region collapses in about a second, while the outer layers are thrown off in a supernova. What's left behind, if it's over the neutron star ceiling, is a black hole of a few to a few tens of solar masses, and some of them appear to skip the explosion entirely. If the star is heavy enough, the collapse can swallow the whole thing before any shock wave escapes, and the star simply stops being there. Astronomers have been watching a small number of candidates for exactly this. One star in a galaxy called NGC 6946 brightened modestly and then vanished, leaving nothing in its place. A failed supernova is a strange thing to hunt for, because the observation is an absence. Then there are the giants. Every large galaxy examined closely appears to have one at its center, weighing anywhere from 100,000 to tens of billions of solar masses. And here's the part nobody can explain properly. In 2000, two separate groups found that the mass of the central black hole is tightly correlated with how fast the stars in the surrounding bulge are moving. Faster stars, heavier black hole, and the relationship is startlingly clean. Why is that strange? Because the black hole is a tiny fraction of the galaxy's mass, often less than 1,000th of it, and its gravitational influence reaches over a region far smaller than the bulge it correlates with. A star out in the bulge does not feel the black hole at all. It feels the galaxy. So how does a small object at the center know how large the galaxy around it is? Or turn it round? How does the galaxy know? The leading answer involves feedback. During its feeding phases, the black hole heats and blows out gas, choking off star formation, so the two grow in step by throttling one another. That's a reasonable story. It is not a settled one. And there's a third category that was missing for decades. In between the stellar ones and the giants, there ought to be black holes of hundreds or thousands of solar masses. And for a long time, essentially, none had been found. Candidates in dense star clusters were argued over for years. The cleanest evidence arrived in 2019, when the gravitational wave detectors caught a merger whose remnant came out at about 140 solar masses, sitting squarely in the gap. That same event caused a different problem. One of the two black holes going in was around 85 solar masses, and stellar theory says black holes in that range should not exist. Stars of the right size to make one are expected to blow themselves apart completely and leave nothing behind. So either the theory needs adjusting, or that object was itself the product of an earlier merger, built up over time in a crowded cluster. There's also a gap at the bottom. Almost nothing has been found between about 2.5 and 5 solar masses in the region where the heaviest neutron stars end and the lightest black holes ought to begin. Nobody knows whether that gap is real or whether we simply aren't good at spotting things there. So the picture by about 1971 is a strange one, but a settled one. Black holes exist. They're described by two numbers. Things fall in, nothing comes out. The area of the horizon can only grow. That last point was Hawking's, proved in 1971. Merge two black holes, and the area of the final horizon is larger than the two original areas combined. Throw anything in, and the area grows. Nothing you can do makes it shrink. He called it the area theorem, and he was rather pleased with it. The pleasure lasted about a year. A graduate student noticed the theorem sounded like something else entirely. The student was Jacob Bekenstein at Princeton, working under John Wheeler, and Wheeler had posed him a question over tea that appears to have been half a joke. Suppose you have a cup of hot tea. Hot tea has entropy, which is the physicist's measure of disorder, of how many different microscopic arrangements would look the same from outside. The second law of thermodynamics says the total entropy of the universe never decreases. It's the most reliable law we have. It's the reason time has a direction. Now pour the tea into a black hole. The entropy is gone. And the black hole has no hair, so it now has a very slightly larger mass and nothing else. The universe's total disorder has decreased quietly in one afternoon. Wheeler said, with evident delight, that this was a crime and that he could conceal the evidence forever. Bekenstein took it seriously. He noticed that exactly one quantity associated with a black hole always went up and never went down: Hawking's horizon area. And he proposed the obvious and outrageous thing. The area is the entropy. Every black hole carries an enormous amount of it, written on its surface, proportional to the area of the horizon rather than to the volume inside. Add the black hole's entropy to the outside universe's entropy, and the second law survives. Hawking hated it, and his objection was a good one, because entropy and temperature come as a pair. Anything with entropy has a temperature, and anything with a temperature above absolute zero radiates. A black hole that radiates is not black. The whole idea collapses on itself. So he set out to prove Bekenstein wrong, properly, using quantum field theory on curved spacetime. He had been prompted partly by a visit to Moscow in 1973. Zeldovich and Alexei Starobinsky had told him there that rotating black holes should throw off particles by quantum effects. Hawking thought their method was sloppy and decided to do it right. He did it right, and it came out backwards. The calculation said black holes radiate, not just spinning ones, all of them. And the radiation is thermal, with a precise temperature. That temperature matches Bekenstein's entropy exactly, including the factor Bekenstein hadn't been able to pin down. Hawking said afterward that he was extremely annoyed. The paper appeared in Nature in 1974 under a title with a question mark in it, and the question mark is doing a lot of work. Black hole explosions, it asked. Then a longer, more careful version followed the year after, and the result has stood for half a century. The explanation you'll usually hear goes like this. Empty space isn't empty. Quantum fields fluctuate, and pairs of particles briefly appear and annihilate everywhere, all the time. Near the horizon, one of a pair falls in and the other escapes. The escaping one carries energy away, and the black hole pays for it. Hawking used that picture himself in his popular books, and it's worth being honest that it is a sketch rather than the calculation. The real derivation doesn't have a location where the pair splits and doesn't need the horizon to be special. What it says is subtler. The notion of empty space is not the same for all observers. During a collapse, the geometry stretches the quantum field modes so severely that what began as a vacuum ends, later, as a genuine thermal glow measured by anyone far away. The radiation is real. The little cartoon of the splitting pair is a mnemonic that gets the bookkeeping right and the physics slightly wrong. The temperature is the interesting part because it runs backwards from everything else you have ever heated or cooled. The bigger the black hole, the colder it is. Temperature is inversely proportional to mass. A black hole of one solar mass sits at about 60 billionths of a degree above absolute zero, not 60 degrees, 60 billionths of one. Now compare that to the universe it lives in. Space itself is filled with the leftover heat of the early cosmos, the cosmic microwave background, which is currently at about 2 7/10 degrees above absolute zero, which means every real black hole in the universe today is vastly colder than its surroundings, and it absorbs far more energy from the background than it emits. All of them are growing. None of them are evaporating. And none of them can begin to, until the universe expands and cools enough that the background drops below their temperature. For a stellar mass black hole that's somewhere around 100 trillion years from now. And once evaporation does begin, the timescales stop being describable in ordinary language. A black hole the mass of the sun would take something like 10 with 67 zeros after it in years to evaporate completely. The one at the center of our galaxy would take 10 with 87 zeros. The universe is currently about 14 billion years old, which is 10 with 9 zeros. There is no comparison to be made. These are not long times in any sense that connects to human experience. They are what happens when a very slow process is asked to finish. But the process does have an end, and the end is peculiar because black holes have what physicists call negative heat capacity. Radiating makes them lose mass. Losing mass makes them hotter. Being hotter makes them radiate faster. So the whole thing accelerates as it goes. Slowly at first, for essentially forever, then faster, then rapidly. And the last fraction of a second releases an enormous burst of energy in gamma rays. Hawking wondered whether small black holes made in the chaos of the very early universe might be reaching that endpoint now, and whether the final flashes might be detectable. One roughly the mass of a mountain, squeezed into the size of a proton, would be finishing about now if it had formed in the first instance after the Big Bang. Astronomers have looked for those flashes for 50 years. Nothing has been found. Primordial black holes remain a live possibility, and in certain mass ranges, they're still a serious candidate for dark matter. But as of now, they are a hypothesis rather than an observation, and that goes for Hawking radiation itself, which needs saying plainly. It has never been detected. It is the most celebrated result in the field, and it is believed by essentially everyone. There is no direct experimental confirmation of it, and no realistic prospect of one. Laboratory analogs have been built, sound waves in ultra-cold atomic gases arranged so that the flow carries them past a point of no return, and those systems do produce the predicted correlated pairs. That's genuinely encouraging. It is not the same as seeing the sky do it. The area theorem, at least, has been checked. In 2021, a group went back to the very first gravitational wave detection. They pulled apart the signal from before and after the two black holes merged and confirmed that the final horizon area exceeded the sum of the two originals, 50 years after Hawking proved it on paper. Now, if the radiation is thermal, we have a serious problem. Thermal means featureless, and the glow depends only on mass and spin and charge. It carries no imprint of what went in. So run the whole process. Take an encyclopedia and a mountain of the same mass. Drop each into its own black hole. Wait an incomprehensible span of time, and watch both evaporate away entirely. Both leave behind identical clouds of radiation. Nothing distinguishes them. The information about what fell in is not scrambled or hidden. It's gone. So where did it go? Is it tucked into the radiation somewhere, too finely scrambled for anyone to read? Or has the universe genuinely mislaid it? Hawking laid this out in 1976 and concluded that quantum mechanics would simply have to be modified. That is not a small suggestion. Quantum mechanics has a rule at its foundation called unitarity, which says the total information in a system is conserved. Nothing is ever truly erased. Scramble a system as thoroughly as you like, and the present still, in principle, determines the past. Burn a book, and the smoke and ash and light carry every letter, in a form no one could ever practically read. But the record exists. Unitarity is not a detail of quantum theory. It's load-bearing. Remove it, and probabilities stop adding to one, and the whole structure begins to sag. So physics split. The relativists mostly sided with Hawking because his calculation was careful and its assumptions were mild. The particle physicists mostly refused because giving up unitarity felt like giving up on prediction itself. The argument went on for the better part of 30 years without resolution, and it acquired a name that suggests something much tidier than it was. The black hole information paradox. The first real crack came from thinking about Bekenstein's entropy again. Notice what's strange about it. Entropy normally scales with volume. Double the volume of a gas at fixed density, and you double the number of ways to arrange it. But a black hole's entropy scales with the area of its horizon. Everything the object can possibly be is somehow accounted for by its surface, not its interior. Gerard 't Hooft in 1993 and Leonard Susskind in 1994 took that seriously and proposed the holographic principle. Perhaps everything happening inside a region of space can be fully described by a theory living on the boundary of that region with one fewer dimension, not as an analogy, as an exact equivalence. In 1997, Juan Maldacena found a concrete case where that appears to be exactly true. A particular kind of curved space-time with gravity in it turns out to be completely equivalent to an ordinary quantum theory without gravity, living on its edge. Every question you can ask on one side has a translation on the other. And the boundary theory is manifestly unitary because it's ordinary quantum mechanics with no black holes in it at all. If the two descriptions really are the same physics, then a black hole forming and evaporating in the interior must be unitary too. On the boundary, nothing unusual has happened. Information cannot be destroyed. It's a proof by translation, and it convinced a great many people. And it is deeply unsatisfying because it tells you the answer without telling you the mechanism. It does not explain how a particular bit gets out. Hawking held out for another 7 years. Then, in July of 2004, at a conference in Dublin, he stood up and conceded. He had made a bet in 1997 with John Preskill of Caltech, with Kip Thorne on Hawking's side, and the agreed forfeit was an encyclopedia. Hawking handed Preskill a baseball encyclopedia and remarked that information could be recovered from it at will, which is about as close to a victory lap as a concession gets. Thorne declined to concede and, as far as anyone knows, still hasn't. The paradox did not go away. It got sharper. In 1993, Don Page worked out what unitarity actually requires and turned a philosophical argument into a graph. Track how entangled the escaping radiation is with whatever remains behind. Early on, each new particle that leaves is entangled with the interior, so that measure climbs. But if the process is unitary, then by the end there is no interior left, and no correlations remain unaccounted for. So the measure has to come back down to zero. And it rises, turns over roughly halfway through, and falls. That shape is now called the Page curve, and every unitary evaporation has to follow it. Hawking's calculation gives a line that rises and keeps rising. It never turns over. That's the paradox, stated as precisely as it can be stated. Then in 2012, 4 physicists at Santa Barbara made everything considerably worse. Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully pointed out that 3 reasonable-sounding assumptions cannot all be true together. 1. The evaporation is unitary. 2. Nothing unusual happens at the horizon, exactly as we established a long way back, because a horizon is not a place. 3. Ordinary quantum physics works fine in the region just outside. The trouble is a rule called monogamy of entanglement. A quantum system can be fully entangled with one other system, and that's the limit. It cannot be fully entangled with 2. If information is coming out in the late radiation, then that late radiation has to be entangled with the radiation that left earlier. But if the horizon is smooth and unremarkable, then each outgoing particle also has to be entangled with its partner just inside. Both requirements at once are forbidden, so something breaks. And if you insist on keeping unitarity, the thing that breaks is the smooth horizon. Cutting those interior entanglements releases an enormous amount of energy, and the horizon becomes a shell of violently energetic particles. They called it a firewall, and an astronaut falling in would not drift peacefully across an unmarked boundary. They would be incinerated at it. That result undid what had felt like the most solid piece of understanding in the whole subject. Polchinski died in 2018. The problem is still here. Progress came in 2019 from Jeff Pennington working alone and from Almhiri with Netta Engelhardt, Marolf, and Henry Maxfield working together. And it came from a direction nobody had been watching. Using techniques built out of holography, they computed the entropy of the radiation properly. and they found that gravity itself instructs you to include certain disconnected regions of the black hole interior as part of the radiation. Those regions are called islands, and including them is not optional. It falls out of the calculation. Do it that way, and the page curve appears. The line rises, turns over, and comes down from a gravitational calculation without assuming the answer. And that is a genuine result. It is not the end. The calculations work in simplified model universes, not in ours. They tell you the entropy behaves correctly without telling you by what physical process a particular bit of information climbs out. And the question of what an infalling observer actually experiences remains open, with serious people holding several incompatible positions. Maldacena and Susskind proposed in 2013 that entangled particles might be connected by tiny wormholes. It would resolve the tension in a way that sounds like a joke, and it is meant entirely seriously. So the honest summary is this: almost everyone now believes information escapes. Nobody can tell you how. Meanwhile, the observers were quietly settling the question of whether any of these things were real. Two teams started the same project around 1995 on opposite sides of the world and did not much like each other. Reinhard Genzel's group worked from the European Southern Observatory in Chile. Andrea Gaze's group worked from the Keck telescopes on Mauna Kea in Hawaii. Both of them pointed at the center of our own galaxy, in the direction of Sagittarius. And both set out to do something that sounds simple and took 25 years. They tracked individual stars. The galactic center is buried behind enormous amounts of dust, so this had to be done in the infrared. And it had to punch through the blur of our own atmosphere. That meant developing adaptive optics, which reshape a flexible mirror hundreds of times a second to cancel the shimmer. Year after year, they photographed the same patch of sky and measured where a few dozen stars had moved. Those stars are not drifting. They are orbiting, fast, around a point where nothing is visible. One of them, called S2, completes a full orbit every 16 years. At its closest approach, it comes within about 120 times the Earth-Sun distance of the center, and it whips around at nearly 8,000 kilometers per second, which is around 2.5% of the speed of light. Both teams have now watched it go all the way round more than once, and in 2018 they caught its close pass. They measured the light from it shifting toward the red, exactly as general relativity says it should when a star climbs out of a deep gravitational well. From those orbits, you get the mass. It's about 4,300,000 times the mass of the Sun, packed inside a region smaller than the orbit of Mercury. There is no known way to put that much matter in that little space and have it be anything else. Genzel and Gez shared the 2020 Nobel Prize with Penrose. Gez was only the fourth woman to receive the physics prize in its history. Then, on the 14th of September, 2015, a signal passed through Louisiana. 0.07 of a second later, it passed through Washington state, and the upgraded detectors had not even formally begun their observing run. The instruments were the two LIGO detectors, each an L-shaped vacuum tunnel 4 kilometers on a side with laser beams bouncing along the arms. A passing gravitational wave stretches one arm and squeezes the other. The stretch they were built to detect is smaller than 1,000th of the width of a proton, which is why it took 40 years and several hundred people to build something capable of noticing it. What went past was the last fraction of a second of two black holes spiraling together, 1.5 billion light years away. One was about 36 solar masses, the other about 29. They merged into a single hole of about 62. Added up, and 3 solar masses are missing. That mass was converted into gravitational waves and poured into space in under a fifth of a second. During that instant, the collision radiated more power than all the light from every star in the observable universe combined. Not one photon of it. It was pure geometry, ringing. The announcement came the following February. The Nobel followed in 2017 to Rainer Weiss, Barry Barish, and Kip Thorne, the same Thorne who won the magazine subscription. Since then, the detectors have recorded well over 100 more mergers, and black hole collisions have gone from unobserved to routine within a decade. And then, we took a picture. On the 10th of April, 2019, the Event Horizon Telescope collaboration released an image of the center of the galaxy, Messier 87, 55 million light-years away, in the constellation Virgo. The black hole there has a mass of about 6.5 billion suns, which makes it one of the largest known. Photographing it required a telescope the size of the Earth, so they built one. The technique is called very long baseline interferometry. You point widely separated radio dishes at the same object at the same moment and record the incoming waves along with an exquisitely precise timestamp from an atomic clock at each site. Then you combine the recordings afterward. The resolution you get depends not on the size of any individual dish, but on the distance between the furthest apart. 8 observatories took part, from Hawaii to Arizona, to Mexico, to Spain, to Chile, to the South Pole. The effective aperture was the width of the planet, and the resolving power was fine enough to pick out an orange sitting on the surface of the moon. And the data volume was so large that sending it over any network was out of the question. It was written to hard drives and flown to processing centers in Massachusetts and Germany in crates. The drives from the South Pole station could not be flown out at all until the Antarctic winter ended. So a substantial part of the observation sat in the ice for the better part of a year before anyone could look at it. Turning that into a picture took 2 more years and 4 independent teams. Each worked with different methods, and each was deliberately kept apart so that nobody could unconsciously nudge their result toward what the others were getting. When they finally compared, all 4 had produced the same thing, a bright, slightly lopsided ring of light around a dark center. So what are you actually looking at there? Is the dark part the black hole itself? And now, the most misunderstood sentence in modern astronomy. That dark patch is not the event horizon. It's called the shadow, and it is considerably larger than the horizon, by a factor of about 2.5 across. The reason is that the black hole bends the paths of the light passing near it, and that bending acts like a lens, magnifying the silhouette. The dark region is the set of directions from which no light can reach you, which extends well beyond the actual boundary. If you drew the horizon onto that image, it would be a much smaller circle sitting inside the darkness. The bright ring is glowing gas, some of it behind the black hole, its light bent around the sides and delivered to us anyway. Woven through it is a thin, sharp feature called the photon ring. It's made of light that went into orbit around the hole 1 or more times before escaping in our direction. In the image, you are seeing the same hot gas repeatedly, stacked up from angles no straight line could ever have carried. The ring is brighter along the bottom. That is not an accident of the gas distribution. The material on that side is rotating toward us at a large fraction of light speed. Motion toward an observer concentrates and brightens the light coming from it, and the lopsidedness tells you which way the thing is spinning. 3 years later, in May of 2022, the same collaboration released an image of Sagittarius A star, the one at the center of our own galaxy. It is far closer, 27,000 light-years rather than 55 million. but it is also about 1,500 times less massive. Those two factors nearly cancel, so on the sky, the two appear almost the same size. Our own was much harder to photograph. Gas orbits the smaller hole in a matter of minutes rather than days, so the scene changes while the exposure is being taken. The team compared it to photographing a puppy. What came out was another ring, another dark center, and another agreement with a solution written down on the Russian front in 1916 and extended by a New Zealander in 1963. Two black holes, differing in mass by a factor of more than 1,000, in galaxies 55 million light-years apart. Both look exactly like the equations say. So, what is still confusing? Quite a lot, and it's worth being clear about which parts. We do not know what is inside. The singularity is not an answer. It's a marker showing where the theory quit. Getting past it requires a working theory of quantum gravity, and after 90 years of effort, we do not have one. String theory and loop quantum gravity both offer partial pictures, and neither can be tested at any energy we can reach. We do not know how information gets out, only that it very probably does. We do not know whether the horizon is the smooth, unremarkable, nothing happens here boundary that general relativity insists on, or whether it hides something violent. So is the horizon quiet, or is it violent? Nobody can tell you yet. The firewall argument has not been refuted. It has been circumvented in model universes. We do not know whether Penrose's cosmic censorship conjecture is true. He proposed in 1969 that nature always wraps its singularities in horizons so that no observer ever has to look at one directly. Nobody has proved it. Nobody has found a convincing counterexample either. Hawking bet on it in 1991, lost on a technicality, paid up, and immediately reissued the wager with the wording tightened. And we do not know how the biggest ones got so big so fast. Quasars have been found blazing away when the universe was only a few 100 million years old, powered by black holes already weighing 1 billion suns. Building one that heavy, that quickly by ordinary accretion, is very difficult. And the seeds may have had to form some other way, perhaps by enormous gas clouds collapsing directly without ever becoming stars. Newer telescopes keep finding these objects earlier and heavier, and the problem keeps getting sharper rather than softer, which is a good place to come back down. So let's come back down. Out past the quasars, past the 55 million light-years to Messier 87, back across the emptiness to our own galaxy, and in toward the middle of it. There's a black hole there, 4 million times the mass of the sun and 12 million kilometers across. It sits in a crowd of stars that whip around it at thousands of kilometers a second. It has been there since before the Earth existed. It will be there long after. Come inward. 26,000 light-years out along one of the spiral arms, there's an ordinary yellow star, and the sun is not massive enough to ever become one of these things. It will swell, shed its outer layers, and settle into a white dwarf about the size of the Earth. It will be held up forever by exactly the electron pressure that Chandrasekhar calculated on a boat when he was 19. It sits comfortably below the limit that would have made all this happen to it. The third planet out, a quiet part of it, a room at night, and you lying still. Your body is holding itself together against gravity right now, and the mattress is pushing back, and your feet are aging very slightly more slowly than your head, by billionths of a second. It's the same reason a clock lowered toward a black hole slows to a stop. The iron in your blood was made in stars that ran out of fuel and collapsed, and some of the elements heavier than that were probably made when two neutron stars fell together and merged, an event we now detect as gravitational waves. And you are orbiting the black hole at the center of the galaxy at about 230 kilometers per second. While you sleep tonight, you'll cover something like 8 million kilometers of that circuit, and you will not feel a thing. Because falling never feels like anything. And in September of 2015, the ripples from two black holes merging 1.5 billion light years away passed through this planet and through every body on it. They stretched you and squeezed you by less than the width of a proton, and then they carried on outward, and they are still going. You don't have to hold on to any of it. Not the names, not the dates, not the difference between a horizon and a shadow. It'll all still be true in the morning, and it was all true long before anybody worked it out. Carl Schwarzschild's equations are still exactly right. The stars are still going round Sagittarius A star tonight, at the speeds Genzel and Gez measured, whether or not anyone is watching. None of it needs anything from you. So let that settle. Let your shoulders come down, and your jaw unclench, and your breathing find its own pace. Out there, 26,000 light years away, something enormous and perfectly dark is turning very slowly in the middle of everything, and it is in no hurry at all. So just rest.